It's fine. All right, so anyway, here we are. And we are in this section, and we started having fun with computing the definite integrals last time. And I believe it was Matt who noticed or brought up that there's sort of a connection here between derivatives and integrals. These aren't two separate topics these are no more two separate topics in calculus than addition and subtraction are two different subjects in arithmetic, or division and multiplication are. They're just opposites of each other. And that's like a huge insight to notice that, like, if you were talking about, if you have some function 1/2 x squared, let's call that f of x, well, the derivative of that is x, right? By your power rule. And in the same way, if you have some function x, the integral of it is 1/2 x squared plus c. Well, that c is a constant, but any constant will do. And that's a huge, huge leap. And it's an important leap. And it turns out it's not just important, it's fundamental. And that's why that section 4.3 is called the fundamental theorem of calculus. Now, if you just sort of go on the internet and say, what is the fundamental theorem of calculus, you get two different answers. Answer one is basically this. The fundamental theorem of calculus is that taking the derivative and taking the integral are opposites to each other. They're like inverses of each other. Yay, fair enough. The other, though, explanation they're going to get is the more mathematical, the more, oh boy, what does this all mean kind of explanation that unfortunately is where homework assignments come from. It's a more, almost like a proof that shows how these things are related. Okay? Now, we're not going to actually do a proof of the fundamental theorem of calculus. But the book does want us to think a little bit harder about this, about how these things could be related. I mean, if I have some function, little f of x. No, let's not use x. Let's call this axis here t. There's a reason why we're going to do that in just a second. You know, we can talk about the area between, like, t equals a and t equals b. And in fact, last time we learned all about doing that. That's what definite integrals were, is they're the area under a curve between some beginning point and some ending point. We skipped, didn't care, whatever you want to say, all the stuff about, well, technically speaking, the function has to be continuous and all that kind of good stuff. We're going to live without that. But we knew that area underneath there is the integral from a to b of that function. In this case, it's dt, because you're integrating along the t-axis. In and of itself, that doesn't seem like that big of a deal. Now, what the book does different then is it says, let's pick this apart. What if instead of from a to b, I had some other spot along here, which I'll call x?
Oh, I know you should put c.
No, there's a reason why we're using x.
Oh, why?
You'll see. I saw that coming a mile away, and I said, will I make that dumb joke? And I said, yes, I will. What about the area from a to x? Well, that area from a to x would be the integral from a to x of f of x dx. I'm sorry, f of t, rather, dt. So we're starting with t equals a, and we're going all the way to t equals x, and and we're integrating. And if we had a different value of x in there, we'd have a different number, a different area, right? If x was a little closer to a, this would be a smaller area. If x were a little farther from a, this would be a bigger. In other words, this is a function of x. We're going to call it big F of x. It is not a coincidence that they chose the symbol big F of x, because remember that was an antiderivative. Remember? All right. So what they're saying here is, we could make a function. We could make this. This is something we could invent. We could make this. We could make a function f of x, where f of x is equal to the integral of some little function from a to x. Where like if x was close to a, we'd have just this little area. If x were bigger, we'd have a bigger area. We could just make that little function. That could be a function. And it's a function. We won't go through all the work of proving that that little function has all the nifty little properties that we wish all of our functions had in order to do things like compute its derivative and so on. Things like it's continuous and all that kind of crap, because I'm sick of that stuff. I want to do stuff with this already. Okay? So we're going to skip all of that and instead say, you know what, if there's some function f of x, you know what I can always do to a function? I can take its derivative. The derivative of that function that I just made, which would be, I guess another way to write that would be the derivative with respect to x of the integral from a to x of f of t dt. That looks really horrible. Except for the fact that integrals and derivatives are like inverses of each other. Taking the integral of some function and then taking its derivative is the same damn thing as like multiplying by 2 and then dividing by 2. Or adding 5 and subtracting 5. Or taking the log and then taking the exponential. All these examples of inverses, this works too. Which means all that we end up with is just this little function. The derivative of this is just f of x. All right, now, to be forgiven for thinking, what the hell? And I'll be honest, I often think, what the hell? I mean, I've had to teach about fundamental theorem of calculus in other classes where we end up using it for something in atmospheric science or whatever. And you go and watch Khan Academy videos about fundamental theorem of calculus. Or you go take the stupid Indiana teacher's exam or whatever, and I took the practice test of that the other day, and there were 3 out of 100 questions were fundamental theorem of calculus questions. But I mean, we can do something awful with it, and that's typically what happens, is that they'll say, the integral from 1 to x of dt of cosine squared t over the log of t. And we want to take the derivative of this. It's x actually here. So here's, that looks horrid.
Wait, then it just be
Yeah,
a function.
it's going to be what? It's just the part on the inside, right? It's just going to be the cosine of the stuff on the inside. I mean, it's just, yeah, it looks horrible. When I took the stupid Indiana practice exam the other day, I couldn't remember how this works, so I ended up having to do the damn integral. Because you're right, if I did this integral, I'd get some, oh my gosh, it was horrible. And then I took its derivative, and then I was like, what the hell is wrong with me? Derivative of an integral. I just spent like 10 minutes on a problem that I could have done in like 8 seconds. The book's going to have that. Whatever. This doesn't strike me as being as important as what we did with definite integrals. Strictly speaking, what we did with definite integrals the other day, where we did something like the integral from 0 to 1 of x squared dx is equal to 1/3 x cubed evaluated from 0 to 1, which is 1/3 1 cubed minus 1/3 0 cubed equals 1/3. That definite integral thing, strictly speaking, is proven using the fundamental theorem of calculus. In fact, I'm sorry, what?
What if we found the integral, but then asked to find the derivative with respect to y, rather than...
Oh, well, yes, then we'd have to be getting into 2 dimensions. We wouldn't be doing something like that until like Calc 2 or Calc 3.
Really?
But it can be done, yeah.
Huh.
So, here's the deal. Some textbooks actually do fundamental theorem of calculus first, and then they show you the definite integral stuff. And some do this when they do the definite integrals, and then in the next chapter they say, at the next section they say, see how we actually, strictly speaking, did it. And both of them strike me as pretty deep into I don't care. Because what we really want to do is those definite integrals. We really want to be able to show how, solve the, well, let's just think about the kind of problems we could solve. If we knew remember how velocity and position are related. If your position is given by 2x, like at time x equals whatever, you're at this position on the x-axis or whatever, then the derivative of that, which in this case would be 2, is your velocity. And you can do it the other way around. You can integrate from there to find, from the velocity, you can get the position. Those things are going to be hugely important in like a physics class or whatever. I want to be able to solve those things. The mathematical niftiness of fundamental theorem of calculus, in and of itself, we're going to do a couple problems about this and we're going to move on. It doesn't strike me as the most important thing, despite the fact it has the word fundamental in its name. It's fundamental in the sense that it's strictly speaking proving the relationship between integrals and derivatives. Okay. Now, one or two things happened along the way that we do have to make sure we know about. You actually had this happen, it was in 4.2, the last section that we did, when they wanted to know, hey, if you've got some function coming through here, between a and b, what is the average value of that function? Like if you wanted to know the average value, like see, some of those values are kind of low, some of them are higher, then there's some lower ones. What is the average value of it? I think you both use the word average like this, f average. All it was the value of that integral from a to b, whatever that function was, f of x dx. And then out in front of it, it's 1 over the difference between the ending and the beginning of the integrals. You both did that before. Your book also, it's part of the proof of the fundamental theorem of calculus, which again we're not going to do. Whatever that average value is, let's just say this is it. This is f average. That's the average value of f from here to here. This idea of how to find the average value of a function is useful. What also is useful is how to figure out where that, or when that average was the value. In other words, what value of c is it so that f of c is the average? And I'm having trouble getting my computer to move for some reason, so I won't quite give you that equation right now. But it's actually what's at the beginning of this chapter, of this section 4.3. Okay? I don't want to write it up there because I'll make a mistake without the book. But you'll just, when you do a problem that involves that, it'll be fine. Hey, this is not going to be so bad. Now, why won't it let me have my computer back? Hey, it's finally connecting. There we go. Hold on. I need to get your assignment. All right. Where is my assignment? Planning calculus? No, that's the problem.
What are you doing?
You okay?
Matt.
What are you?
Talk about Matt.
Matt's got his thing on there.
That's gonna.
Well, all right. I can't get it to bring up the worksheet where I wrote down the assignment, so I'm going to write down a new assignment. I think it's just because the network is down. All right, so we're on page 562,
Naturally.
and we're going to do, how about all problems?
How about now?
What kind of ideas are?
How about, okay, the first one's coming, ones are easy. How about 149? Matt, I feel like you're dealing with stress in an inappropriate way.
The way I deal with stress is probably not this.
Tell me how you deal with stress, Matt.
Bitter.
You get bitter?
I'm bitter and spite. Yeah.
We're trying to roll the time over here.
171 through 187. Okay, here's the deal. This group of problems right here says solve these using the fundamental theorem of calculus. Just evaluate the integral, the definite integral. Okay? I don't want you to actually, like, somehow do it, rewrite it in the form of a, no, just do the definite integral. Okay? And I will deal with the fact that my computer will not connect to. Bill Cosby was just found guilty on 3 counts. Holy smokes.
About time. Oh my gosh, they could not have drove.
Oh, we were dropping the camera before we start talking about Bill Cosby.